Hello students, this is lecture number 12B. Okay. So far we have looked at two methods. The first was Galerkin method of finding the approximate solution. The second was the Rees method. Yeah, so methods, and we have seen that both of them start from different equations and from there it is derived. Yeah, so they solved same problem but differently. Their start points are different. So for Galerkin we start from the weak form of the differential equation. For Rees we start from the minimum potential energy expression. From there we minimize u, right. So we minimize the potential energy by varying u and we find u, right. Okay. So today we will understand a little bit more physics and mathematics with the Rees method, with the minimum potential energy method, right. So so basically if we have like in the previous lecture video we had the potential energy expression and we wrote it something like this: 0 to L, then we said a half, then E A, then we had a du over dx square dx, and then we had the work. So we had like B multiplied by u, right, and then dx. Yeah, so this is true for this example where there is nothing at the end. So if you have this B, that's it, there is nothing at the end, then we can write this way. Yeah, okay. So for simplicity I have taken this, I have not taken the end force like this one. Yeah, so this now the thing is I want to show that this equation is nothing but the same as the strong form. So we can actually formulate the strong form and weak form from here. Yeah, so we can get the weak form, for example, very easy to get from here. Yeah, okay. And how can we get that? Okay, so let us say this is also like there is something called variational calculus. Okay, so variational calculus which actually talks about this kind of function. So this is a function of functions. So this is basically nothing but is you call functional, meaning function of a function, right. So function here is phi potential energy, and of a function here is ux. So basically this is a functional of function u, right, which is u varies with x. So in variational calculus, like the boundary value problems can be represented as this functional, and the solution of which is the u which minimizes this functional. So this is same as saying that you minimize the potential energy to get u. Yeah, so there is no difference, it is the same thing. Only thing is when you say potential energy, this is true only for a stress analysis problem. When you say it is a functional, then it becomes applicable to all other kinds of problems as well. For example, heat transfer problem or diffusion problem can also be written as this functional, and the solution like finding the temperature in heat transfer problem will be just by you minimize this functional, and whatever u minimizes this functional will be the solution of that heat transfer problem. Yeah. Okay. We will see later on that this is because the expression, the differential equation that we get for a heat transfer problem is very similar to the stress analysis problem, and hence this is true. Okay, so let us start with this one and let us see whether we will be able to find out the weak form or not. Let us start from there. Okay. Now, we know that the solution of this functional, right, the solution u of this problem is the one which minimizes this functional, right. Okay. So, let us see solution, your solution is u, assume solution or approximate solution, right. Some approximate solution is u x, yeah. Then you are give little bit some perturbation, yeah, you are giving little variation. So, little variation, give little variation, okay. Let us say delta u, yeah. So, what happens? Your initial you can say the u1 x, well, let us not write u1, but initially it is ux, which is already a solution, right. And then and after you give little variation delta u, your u becomes, after variation you have ux plus delta, let us call this condition 1, this is state 2, we have delta u ux plus delta u, like this. Now, we will assume delta u equal to zeta w x, yeah, where zeta is very small, very small. Okay. We can write that since this is the phi is a functional which is a function of a function, hence there will be a variation in the function itself, and the function is ux. After variation this becomes u plus delta u, where delta u, since u is a function, right. So, you can write it delta u equal to a zeta multiplied by w x, where w x is a function, right. So, w x arbitrary function, right. Okay. Now, the next thing is what we are going to do is we can see the variation in, so variation in the potential energy or functional, in the functional phi u x will be equal to, or let us call it delta phi will be equal to, first we will write as phi u plus delta u minus phi u, right, which is equal to 0 to L, right, 0 to L, and then we have u So, we have E half E A, then we have d over dx, and we have u plus del u, right. Then you have square of that dx, right, and then we have minus 0 to L b u plus del u dx. Then we will have minus 0 to L half E A, then du over dx x square dx minus 0 to L b u dx. Okay. Now, this del u is nothing but zeta times w x, right. So, in anyway we want to expand that, right. So, if you expand that, what happens? These terms becomes du plus, here we have zeta terms coming here, right. So, we can spell that out. So, we can write as equal to, yeah, okay. So, in this case we will have, so let us spell it out maybe in the on the next page. So, we write equal to, or say del phi is equal to 0 to L half E A, and then we will have d u over dx plus zeta dw over dx square dx minus 0 to L b u plus zeta w dx, right. Okay, guys. So, here it should be plus, yeah, because this minus this, so minus becomes plus. So, since this is plus here, so we have minus here, minus here, should be plus here. Okay, okay. So, then we have minus 0 to L half E A du over dx square dx minus 0 to L bu dx minus zeta, sorry, no zeta here, only plus. Okay, that is it. Okay. So, we have that. So, we can expand that further, and you can see here the square, if you square we get du over dx square plus 2 times zeta del u over del x multiplied by du dx plus zeta square dwx whole square. Okay. So, instead of writing more steps, we can see that the first term du over dx square term, because of this, and we have the same thing here. So, they cancel out. Same thing here, if you see here we have bu times b zeta w. So, bu term is here, also bu terms. So, minus plus they cancel out. So, we will have zeta w term from here remaining. From here we will have 2 zeta dw over dx times du over dx plus zeta square term, right. So, we will just write the final term, and what do we get? We get half 0 to L E A, and then we get, let us write like this, 2 zeta dw over dx times du dx plus zeta square dw over dx square dx, yeah, and then we will have minus 0 to L b zeta b w dx, yeah, okay. Okay, but we have zeta which is very small, since zeta is very small, zeta square can be taken as 0. Okay, so that means this term will go away, and what we will have is simply this. So, half times 2 zeta, so becomes zeta only, and then Ea this term, and then we have from here also zeta common. So, we can write, or del phi over zeta we are taking here is equal to 0 to L, and we will have Ea, okay. Then let us write like this, then you can recognize the form, then we have dw over dx Ea du over dx minus, we have done that, and then we will have minus 0 to L b w dx, okay. Okay, so we got that, yeah, okay, we compare. So, zeta and zeta from here we have taken here divided by del phi divided by zeta, and then whatever is remaining after making zeta square equal to 0, we get that term. Now, since ux is already a solution, already a minimizer of the functional phi ux. So, a small variation in x will not change the value of phi ux. Hence, del phi should be equal to 0. That tells us that del phi over zeta should be equal to 0. That tells us that simply this whole term should be equal to 0. So, this will be 0 to L dw over dx Ea du over dx right, minus 0 to L bw dx equal to 0. And what you see is the same weak form we got, right. So, if you see the previous lectures, maybe lecture 11, yeah. So, we had got a weak form, yeah. So, this weak form what we got there, it is the same weak form you are getting here. So, this is actually the weak form. Okay. So, this is actually the weak form. So, what you see here is actually there is no difference between our equation in the form of potential energy, okay, like this one, this, and the weak form. So, this is actually you derive this is energy method basically. So, you are expressing u in terms of energy, and the solution will be the one which minimizes the energy, potential energy. And in the other case here, this is the in the form of the change in the functional. Yes, this is a little bit mathematical point of view, right. So, we said this is a functional, phi is a functional, and the solution is a function which minimizes phi, and then you try to vary u little bit. Since function is at the minimum, then the slope, so means there will not be any variation in phi if you change u little bit, because it is already at minima, right. So, any variation is phi has to be 0, and hence you are getting the equation, and that equation turns out that this equation is the weak form. Okay. Okay. Now, earlier when we started from the strong form, so like right, so we had the strong form, right, and this is for the same equation, and we got this strong form as d over dx Ea, then du over dx plus b equal to 0, and plus the boundary condition. You have the boundary condition like this. So, you have b going like this, yeah. So, you had boundary condition, and you had u at 0 equal to 0, and Ea du over dx at x equal to L was also 0. Yeah. So, this was the boundary condition you applied. So, this is the strong form. Now, we treated the strong form as a mathematics. From there we went ahead, but weak form also has a meaning basically. So, this has a physical meaning, and since the origin of the finite element analysis goes back to the development of mechanics basically. So, it is there is a lot of contribution was made to mathematics by the physicists. Physicists that time was basically working on this mechanics problem, that is elasticity problem and all. So, you will see that even the functional we call it, but actually it has the potential energy form. So, the weak form also there has to be something there. Basically, if you see, this equation is nothing but it tells you the way we derived, this is the total force equal to 0, right. So, we said total f x equal to 0, and in derivation, if you remember, we had like this, right. So, we had sigma that was E du over dx, sigma term here, and then sigma term here, right. So, but okay, so let me write correctly. So, we had sigma a term here, not like that. So, sigma a here, and we had sigma a plus d sigma a over dx times dx. So, we had this kind of things. So, then we had b also here. And then we find out what we did. We did the total force F x equal to 0, right, and hence this 0 is coming from that, and this total force F x, that gives you this equation. Now, total force F x, let us say it is not equal to 0, right. If it is not equal to 0, then what happens? Then there will be some work which is done, right. So, basically also known as the virtual work. Right. So, virtual work is nothing but total force Fx multiplied by some virtual displacement, right. So, here del u virtual displacement, right. Okay. Now, the principle of virtual work says that if the structure is already in equilibrium, yeah, so any small amount of u is not going to give you any work, right. Work will be 0 because it is already balanced basically, and hence there is, if you apply the displacement, and then it will give you a 0 work, because actually there is no work, because forces are balanced. See here that del Fx equal to 0. So, force is equal to 0, and hence this force will not, since force is 0, hence applying one displacement is not going to change anything, it will not do any work, and based on that we can actually do something there. So, a strong form, this part is nothing but summation of Fx, and this is at every point. So, that really means we can say virtual work equal to virtual work, or we can say dW is equal to, in this case will be simply d over dx Ea du over dx plus b, and we are multiplying with del u like this. Okay. Okay. Now, this del u we also wrote it as okay. So, here I think instead of writing w, we should write something else. Okay. So, because we will be confused, we also said u as a small zeta wx, right. So, let us call it something else. So, let us call it v, okay. So, instead of saying dw, let us call it dv is the virtual work. Okay. Okay. So, we have delta u here. So, delta u is nothing but, remember we had delta u was as zeta w, right. Okay. So, zeta w that we have for del u, we can replace this delta u with zeta w here. One thing also, that remember that we have derived this, this is gives you b, for example, is force per unit length. Yeah. So, in fact, this is force per unit length. Yeah. And this is because we also have dx multiplied both the sides, but that we have removed, and hence summation of Fx, in order to get that you have to multiply it by dx as well. Yeah. So, virtual work will be dB equal to this multiplied by you should have multiplied by dx as well. Okay. So, we will have dx as well here. Okay. Now, since we have del u over zeta w, hence we can write virtual work dV is equal to, we have d over dx and then EA du over dx plus b multiplied by delta u, which is equal to zeta w. So, we can write zeta w, which is a function of x, yes, and then we have dx as well, right. So, dx is because so that we make it force, but not force per unit length, hence we have dx term here. Okay. So, what you see here in this case, we have the total virtual work will be equal to 0 to L dV will be equal to 0 to L, and zeta we can take it out, and we have W x multiplied by d over dx, then E A du over dx. Now, it is found, it may sound familiar to you now. So, what you see here plus b term, this b will also be there. So, okay, so just write plus b, right, dx. So, this one you have seen earlier. Okay, this is how you start the you have multiplied, this is the you call it residual earlier, right. So, this is residual multiplied by weight function, and then you are integrated over the whole length. So, this you know that finally this will be equal to, you can say, okay. Now, this total virtual work has to be equal to 0. This is as per the principle of virtual work, and hence you get this 0 to L W x d over dx E A du over dx plus b dx equal to 0, which is actually the weak form. You expand that and you will get the weak form, and we have seen that, right. So, this is nothing but the weak form. Okay. So, here we see that actually from starting from the minimum potential energy, you can get the weak form. We did mathematically, basically knowing the definition of the functional minimum potential energy is nothing but the a functional basically, and which is minimized by the displacement, solution displacement. In this case, we are starting from the strong form, and then we have applied the physics or the solid mechanics basically, and in this case also we are getting the weak form. So, basically the idea was to show that there is a physical meaning of the weak form, and this is simply tells you this is the virtual work. So, it tells you that virtual work has to be equal to 0. This is what it tells you.